Hello and welcome to the Classical Knot and Virtual Knot Star seminar. My name is David Freund. I'm a preceptor at Harvard University, and today I'm going to be talking about some algebraic structures for flat virtual links. First, though, I would really like to thank the organizers for inviting me to give this talk, and I hope that everyone is doing well. So the big idea is that we're going to be studying generalizations of curves on surfaces, which are called flat virtual links. And I want to use this time to give an overview of some different algebraic constructions in flat virtual knot theory. And if you have any questions or comments, or if you want to talk to me about any of this, please don't hesitate to reach out. So throughout the talk, I'm going to be working in the smooth category. All of our surfaces are going to be oriented and compact. And anytime I refer to a curve, what I'm really referring to is an immersion of a circle into some surface in general position. And one of the reasons you might want to study these objects is because they lead to invariance of virtual links. So any invariant of a flat virtual link is necessarily an invariant of a associated virtual link. Now, maybe that's enough for you, maybe that's what you care about, but what I'm really interested in are the ways in which these invariants can be used to distinguish families of curves on surfaces. So the invariants that we're going to build, since they're coming from something that is effectively a collection of curves on a surface, you can distinguish between a couple collections by using them. At least that's the idea. So to kind of put this on firmer ground, we have a few different ways that we can represent flat virtual links. The first of which is by using curves on surfaces, which gives us a nice geometric picture. But we can also use Gauss or chord diagrams to study these objects combinatorially. And this connection between curves on surfaces and these more combinatorial diagrams goes back to Gauss. But what makes things possible now is a result of Carter, Kamada, and Saito, that actually we can go back and forth between these two representations in a nice way. And the third way that we could study these is by using planar diagrams. So using the more classic knot diagram, where you have no over-under structure at crossings. Instead, you allow for a second type of crossing called a virtual crossing, which somehow captures crossings that aren't really there. And what that really means is that if you move this to a surface, you might have what would appear to be crossings from a projection that occur between a curve or a pair of curves on different sides of a handle. But I really just want to focus on the first two models here, where we can see some sort of connection between them by thinking that each curve on the surface is represented by some circle, and then the intersections between the curves, or self-intersections, are represented by an ordered pair of points, better visually represented as an arrow. So we need to talk about how to make this jump between the two, and then we'll be off. So to move from the curve on surface picture to something more combinatorial, let's just give labels to our intersection points. We can draw a core circle for each loop, and then the real essential thing here is marking the cyclic order of points as you traverse each curve on the surface. So for instance, if we follow the green arrow, or the green curve, starting at the arrow, then the first point we would encounter is A, then C, we loop back around to B, then C, and we're back to A. So on the core circle, we want to go A, C, B, C, and now we're back at A. So doing this for each of your loops, now you have your distinguished collection of points on the circles. What we need to decide on is the ordering of points. And to do that, we want to look at positive or negative bases of the tangent space, where we're thinking about a positive basis, where we're thinking of the first element of the positive basis being the tail of your arrow and the second element being the head. So for what this really means is when you get to an intersection, there's two forks you can travel along, the left or right fork. And if you follow the right fork, then this is marking the tail of your intersection. Whereas if you cross the left fork, then you're following the head, or you're marking the head. So for instance, for intersection A, the blue curve is coming down as the right fork, the green is coming across as the left. And so on the A side, we should get the tail of our arrow, and on the green side, we should get the head. And then you just do this for all of your different arrows, all your different intersection points, and now you've got your chord diagram. To go the other direction, what you want to do is take a projection of your chord diagram where you identify the points that are connected by arrows so that you preserve the correct orientations. This is now giving you a four-valent graph, or four-regular graph, which you can then thicken into a disk band surface, and which the curves live as the core of that surface. And then you can cap off the boundary to get a closed surface if you want that. But honestly, that disk band surface that you get is exceptionally useful. So now that we've made this connection, we also need to think about the equivalence of different representatives of a flat virtual link. So we're focusing on our two models. On the geometric side, we have flat Reidemeister moves, so just ignore any over-under structure at crossings, and keep in mind these are supposed to be oriented, but because of the different variations you get, I left that off here, which will feel contradictory compared to what I'm going to do in the combinatorial model. But this actually isn't enough. So these would just give you homotopies on surfaces, and that isn't a strong enough relation to let us move into the combinatorial model completely. Instead, what we need to be able to do is change the surface. So we have to allow for stable equivalence where we add or remove empty handles that are disconnected from the curves on the surface. And now if you wander around using flat Reidemeister moves and stabilizations and destabilizations, you've got the correct object. And on the combinatorial side, you get a collection of chord moves. So the type 1 chord moves represent the different Reidemeister 1 moves you could perform. And to be clear, what's happening is you have this empty arc here. There are no arrows, no endpoints of arrows in that arc. And what you can do is add an arrow in one of two ways to this otherwise empty arc. Or you can remove that if it's the only arrow there. And this is analogous to introducing a kink, like with the type 1 move. For the analog of the Reidemeister type 2, you want a pair of arcs on your core circles, which you then add oppositely directed arrows to. Now there's 4 different configurations if you live on the if both arcs live on the same circle, you get more combinations. If you're also looking at one arc living on a component, each arc living on distinct components. The analogs of the type 3 moves are the 3A and B moves. And what's happening here, in a sense, is you end up switching the arrows on each of these otherwise empty arcs. And that's the analog of a type 3. Now, what's hidden in here is that for operations like the Reidemeister type 2 move, it's not enough to just move that to the world of the type 2 chord move, because this encompasses a lot more possibilities. You might need to combine this with stable equivalences to actually achieve the Reidemeister 2. But in either approach, if you have some representative of your flat virtual link, then we're really talking about the virtual homotopy class of that representative, where we're either quotienting by the flat Reidemeister moves and stable equivalents, or we're quotienting by these chord moves. So now we have an object to study. We're looking at collection of curves on surfaces up to these equivalences, or chord diagrams up to analogous equivalences. The fact that these are actually equivalent theories is a result of Carter, Kamada, and Saito from 2002. So for what we're going to do for the rest of today, there's kind of two branches of motivation. One is using this more geometric approach of curves on surfaces. And here, Andersen-Mattes-Reshetikhin defined a bracket on homotopy classes of curves, which determines a lower bound on the minimal number of intersection points between any pair of curves on a surface. But in 2013, Kahn and Chernoff proved that this lower bound is actually sharp. So we need to be a little careful with that, but this is a great tool for trying to capture the minimal number of intersection points. That would be a nice thing to bring to flat virtual links. And we'll see that we get some similar results depending on what we do. The other side of this is building off of work of Turayev, which is motivated by classical knot theory. So if you look at the homological intersection form on the ciphered surface of some link, then using the correct construction, this gives rise to the ciphered matrix of that diagram of the link. Now, what you need to be careful about, and I feel like most of the time we're interested in the ciphered matrix because under the correct determinant of it, you get the Alexander polynomial. And the reason that we're moving to a polynomial, some kind of invariant, is because the ciphered matrix itself is not invariant. So we can change the ciphered matrix, but this goes to work of Levine and Schroeder. If you take any two ciphered matrices, then they're S equivalent, meaning that there's a pair of operations which correspond to the addition or removal of empty handles. You just need to carefully modify the homology, the basis for homology, and then what the matrix ends up being. So now if you take this S equivalence class of ciphered matrices, that is a link invariant. And what's really cool is if you start playing around with that S equivalence class, then there's a minimal collection of ciphered matrices for any given link, and you can use those to get some additional information compared to what you might have gotten from the original ciphered matrix. So this gives us two different things that we can look at to try to extend into the flat virtual link setting. I'm going to start, before we dig into that though, just to really outline our goals, we need to talk about minimality for flat virtual links, because there are some key differences here that give us some extra information that we can leverage in other ways. But then I do want to extend the AMR bracket. I'm going to construct based matrices for flat virtual links. And then in the last section, I want to use primarily the results from sections 2 and 3 to bound or compute the minimal number of intersection points between two components of a flat virtual link. So to get started, just to really emphasize some of the properties you might look at in a flat virtual link, I never promised that the supporting surface for the flat virtual link would be connected. And if you add empty handles, you could always connect two different connected components to get a representative on a connected surface. But that's somehow not as interesting, because, using destabilizations, you can also cut out empty spheres or empty surfaces of higher genus. But what's really interesting is the maximal number of connected components you can break your surface into, each of which has some number of components of your link. So that number is an invariant for your link. And you might also think about the genus of this supporting surface, where for a disconnected surface, we would sum the genre. And then we can also look at the number of intersection points, whether these are self-intersections or occurring between components of your link. For most of today, I'm going to focus on two-component flat virtual links and talk about the minimal intersection number, beautifully abbreviated as min, to be the minimal number of intersection points that occur between your two components in any representative. So this is your analog of a crossing number in the flat setting. But what makes this so different from thinking about crossing number or thinking about virtual knots is the fact that we don't have to worry about an over-under structure. This gives us considerable freedom to manipulate the diagrams or the representatives of a flat virtual link. And while we could just look at any geometric representative or any combinatorial representative and get an estimate on the minimal intersection number, we're really doing ourselves a disservice if we don't use the combinatorial model as well. But in some results that are still under review, I was able to show that for a large family of flat virtual links, and these are ones which must live on a connected surface. There is no way to move them onto multiple surfaces. And then this non-parallel condition is saying, in essence, you don't have any pairs of curves in any representative which are homotopic to each other, or to homotopic to powers of some primitive curve. But what I really want you to think about now is we have some n-component flat virtual link, and we're able to get a minimal representative of this link. And by that I mean it has minimal genus and the minimal number of total intersection points, which we can obtain monotonically from any representative. So this is very different. So we don't have to worry that we're somehow going to get stuck at a local minimum in terms of either genus or the minimal number of intersection points, we can get to this minimal representative in a greedy fashion. We can just reduce anytime we see an opportunity, and we're going to get there. But that's not enough. So we've monotonically achieved this minimal representative. It's actually unique up to moves that don't change the number of intersections. So if you have any two of these minimal representatives, then they're related by a sequence of type 3 moves. You never have to increase genus or the number of intersections. So as a corollary of this, even if you're not on this connected surface, you get this minimal representative, but there's no longer a guarantee you could achieve it monotonically. But it's there. So here we have a pair of homotopic, or a triple of homotopic curves on a genus 2 surface. And we can exchange these two components here, red and green, which maybe that was not the best color scheme for this. I apologize. I will fix that. So if we exchange those two, that's fine. Unfortunately, the only way to do that is by using a type 2 move in the middle. So you can't just move between these using a type 3 move. And based on these results, there's actually no guarantee that was a minimal representative to begin with. So with students at Yale last summer, we worked on this problem, and they found that if you have any flat virtual link, then there is a minimal representative, which we believe can be obtained monotonically. So we're still writing up this results, and it was a lot of fun to work with them, and I think they should be really proud of the work they did. But this is exciting. This is so different from what you see with classical knots or virtual knots. There's somehow not a great way to get these minimal representatives in some kind of reasonable time. Here we get this monotonic reduction of genus and the number of intersections, which is achievable practically. So that's really fun. But now we want to think about some of our other goals. So these minimal diagrams exist, these minimal representatives. Let's try to extend something from curves on surfaces to the flat virtual link setting. And I should say that there's already been an extension of the Goldman-Lee bracket to flat virtual links. You can think about Turayev's co-bracket, which Patricia Kahn extended to flat virtual knots. And so there's some of these additional constructions you can think about. I'm just going to focus on the AMR bracket. So what we're doing here is we're taking a pair of curves on a surface. Boy, does that sound familiar. And we're considering them up to homotopy on that surface. And what Andersen-Mattes-Reshetikhin did is they considered the different wedges associated to the pair of curves. So at any intersection point between the two curves, you can consider the wedge at that point. And associated to that intersection point, based on the order of your pair of curves, you can designate a sign to it. And the AMR bracket is really taking the sum over the different intersection points, take the homotopy classes of wedges at the specified point, and weigh it by the sign of the intersection point. So now we have an element of a free abelian group, and if you look at it is possible that on your surface, a pair of wedges are going to be homotopic, at which point you might see collapsing in this operation. But when you do, you're getting something that's reduced. So if you look at the reduced representative, then you're going to have different positive, zero, negative values out front. And if you take those in absolute value and add them all together, you get the terms of your bracket. And Kahn and Chernow proved that the terms of this bracket counts the minimal intersection number of a pair of curves. Now, you have to be a little careful if you have a pair of curves that are actually homotopic to each other. Then the AMR bracket is going to vanish. And so to get around that, what you can do is reverse the orientation on one of the curves. And so long as they're no longer homotopic, you get to count the minimal number of intersection points. So this is a fun result. This gives us a way to at least think about the minimal number of intersection points. How much collapsing is there, or what's left when you look at the AMR bracket? So we want to extend this to flat virtual links. So the idea of a pair of curves, that's fine. If you have a wedge, then we need to start thinking about virtual homotopies that include the wedge point. So these come in two varieties depending on whether you're looking at the geometric or combinatorial perspective. The singular type 2 move allows you to move this distinguished point, this wedge point, across a bigone, or you can move a strand across the distinguished point. There's no harm in doing that. On the level of chord diagrams, this means you're switching which arrow is distinguished. So from here, we're going red being the top arrow to the bottom. And then for the type 3 move, you get the same sort of operation. And this distinguished point, I think from here on out, it's just going to be designated with a D for distinguished, but it's possible I'll still use P as necessary. And then the virtual homotopy class of these wedges is unambiguously denoted in the same way. So now we have the correct object, and what we need to start thinking about is how to generalize the Andersen-Mattes-Reshetikhin bracket. So signs of intersections, whether they're in the geometric or combinatorial perspective, are fine. We have wedges, we have singular virtual homotopies. What we need is to actually extend the bracket. One way you can do this is perhaps the most natural one that I could come up with, and that's you take the element of the free abelian group on virtual homotopy classes of wedges. So let's take each intersection point of a representative of our flat virtual link. Consider it wedged at the point P, take its virtual homotopy class, and weigh that by the sign. This seems like a very reasonable definition, where we've notationally just added subscripts of V everywhere. But if you go through, this is something that's well defined for flat virtual links. But that's not the only definition. So with Chernow and Sadikov, we came up with another definition of a strengthened AMR operation where it looks identical. I've got a subscript of S for strengthened, but we're still looking at some virtual homotopy classes. And the distinguishing fact here, or the distinguishing definition here, is instead of just letting these virtual homotopy classes wander around however they want, we want them at every instance to be realized on the same surface. So, I think the first definition is reminiscent of Andersen-Mattes-Reshetikhin's operation. This one, in other ways, really captures the essence of their definition. So any virtual homotopies we apply, if we're going to stabilize or destabilize the surface, we have to do that for all of the wedges simultaneously. And that gives us something that's a little more rigid and gives us a better way to connect this back to the original AMR bracket. But in both of these cases, despite the notation, this is not an operation on a pair of virtual homotopy classes. So this is not taking the virtual homotopy class for a curve along with the virtual homotopy class of a second curve and smushing them together. That unfortunately doesn't make sense. You really have to take the virtual homotopy class of a pair. So that being said, when you're looking at these pairs with the virtual AMR, where we let the virtual homotopy classes wander around, unfortunately it vanishes anytime you can use a virtual homotopy to exchange the order of your two components. So for instance, in what I've come to call the double Cashino double, it's a two-component version of the flat Cashino double. If we perform a rotation on this flat virtual link, then you end up just exchanging the components. So now that means the virtual AMR is going to vanish here. And even in other cases, if we want to compute this operation, then what we need to be able to do is distinguish between virtual homotopy classes of wedges of curves on surfaces. So we're trying to distinguish singular flat virtual links. And there's not a lot of invariants out there for doing that, but we're going to talk about one momentarily. Now, for the strengthened AMR bracket, it turns out that what you need to be able to do is compute the original AMR bracket. That's what it boils down to. If you can compute the original AMR, then you have a way to compute this strengthened bracket. But that means we're not going to be relying on this combinatorial structure. So that's definitely an off-putting side of that construction. But on the other hand, Chernov, Sadikov, and I proved that in actually weaker conditions than this, then the minimal intersection number is counted by the terms of this strengthened AMR operation. So even though it's not the best in terms of using the full structure of flat virtual links, it does mirror Kahn and Chernov's 2013 result about the AMR bracket. So this gives us an operation, but what we need is to be able to distinguish these singular virtual links. So now I want to turn to the promised analog of a Seifert matrix, which originally dates back to Turayev in 2004, where he defined a based matrix for what he called a virtual string, but it's really a flat virtual knot, which Alice and Henrich extended to singular flat virtual knots in 2010, and Kahn further extended that to signed singular flat virtual knots, which we're not going to get into. But we have this construction which has been built up that we'll see as analogous to the construction of the Seifert matrix. And then 2019, Nick Petit generalized base matrices to flat, long or framed knots, virtual knots, or singular versions of them. But my contributions, this is now available on the Journal of Knot Theory and its Ramifications website, but this result is really going to come through in a paper I hope to have in the archive in the next couple weeks. So what I want to do is extend this to links, because everything else had to do with knots. I want some kind of algebraic structure for flat virtual links instead. So the basic idea is we have our representative, we have our chord diagram of a flat virtual knot or link, and what we're going to do is build an object from the canonical surface that you associate to the knot or link. And then we're going to look at the homological intersection form on that surface with respect to a canonical basis, which is going to come from the intersections or self-intersections or intersections between loops of that representative. And then from there, we're going to get a number of properties. So all of these base matrix constructions have something like this in common. You're able to combinatorially compute the intersection form on your canonical basis combinatorially under a collection of operations arising from virtual homotopy. You get operations on your base matrices. You get mirroring operations on your base matrices. And then there's some kind of existence and uniqueness of a minimal base matrix from which you can derive a whole host of properties about your flat virtual knot or link. So that's the big picture. We're starting with something and we're going to build our matrix by using a canonical basis and looking at the homological intersection form on that basis. So let's start that. To build this basis, we're going to want elements that are corresponding to each curve on your surface or each coarse circle. So for instance, if we just take this blue component, that corresponds to a loop in your canonical surface. And we want to keep track of that. There's a lot of information there that's useful to hold on to. But then for every other arrow, we want to associate arcs of your coarse circle, which then project to cycles in homology in your canonical surface. For self-intersections, this isn't too bad. Start at your right fork, follow the curve until you get back to your intersection point. That's it. That's your cycle. On the level of chord diagrams, you are traveling around an arc that goes from the tail of the arrow to the head. For intersection arrows, though, you need to be a little bit more careful, because if I just left along the right fork of this intersection point and followed it along, I would traverse the entire blue curve and come up here. And that's not a problem. That's a copy of the blue curve. But then any intersection point which has the blue arc as the right fork is going to define the same thing. So that's not a basis. And similarly, if we travel along the left fork, we would just follow the green curve. So somehow we need to split it up. In my paper that's on in the Journal of Knot Theory and its Ramifications online at the moment, I treat these discretely. So the self-intersections, you can treat them with these cycles and really hold to Terayev's original construction. And then for intersections arrows, you somehow treat them as, does the arc for a self-intersection see that intersection point or not, see that intersection arrow. And that's enough to give you a based matrix structure. But in the interest of building something for singular based matrices, or for singular flat virtual links, we have another option. We can use the distinguished arrow as a canonical point at which to change the path we're following with our arc. So let's include it, and then let's start at the right fork as we have, and follow along until we get to the distinguished intersection. At this point, we're going to switch forks. If we came in naturally following what would lead to the right fork, we're going to switch to the left, as in this picture. Or if we came in on what would normally be the left, we'll switch to the right. So however you switch the component you're on, and then you can follow that curve until you get back to your original intersection. And on the chord diagram, this is defining a pair of arcs. And the way you want to think about this is you're going from the tail of your intersection to the distinguished arrow, and then from the distinguished arrow to the head of your original intersection arrow. So this is how we can get our cycles, and it turns out that this is a good basis on which you can compute the homological intersection form. So to be very clear, the singular base matrix, the SBM, for a singular flat virtual link with two components is going to be a sextuple of data, where the first three sets are really capturing the basis of your homology. Then S1 and S2 are your representatives of your different curves. And then B is your homological intersection form. And we get this basis by looking at the arrows in the chord diagram. And to make the count work out, there's one that we have to exclude, which naturally should be D, because it's a little ambiguous how the cycle for it should be defined, and it wouldn't be linearly independent with S1 and S2 regardless. So with this, we have a way that we can combinatorially compute, which I'm going to go through very quickly, because this is kind of moving away from my desire of giving an overview of these objects. But just for completeness, to actually compute the intersection form, you want to know how many arrows have their tail in the arc of, say, A, and have their head in the open arc for B. So that would contribute a positive intersection point if you look at this geometrically. And then you want to subtract off any times that the head of an arrow is in the open arc defined by A, and the tail is simultaneously in the open arc defined by B. And then you have to introduce a little fudge factor, because in that definition above, we're looking at these open arcs, so we're necessarily excluding A and B themselves from somehow intersecting each other at the points A or B. So we need to just work with that carefully, and this epsilon term adjusts properly in most cases. But for intersection arrows, you also have to worry about what's happening with the distinguished arrow in a similar fashion. And then what I've been able to show is that using this dot of any two arrows, and then these kind kind of adjustment factors of epsilon and delta, we can compute the singular base matrix. But once you've computed it, that's really not enough. So here's an example. Here's a singular base matrix for this pair of curves. We're going to label everything. So here is our distinguished intersection. G1 and G2 are self-intersections. X1 and X2 are genuine intersection points. So here you go. Here's your singular base matrix that's associated to this pair of curves. And if you look, and this is actually general, although doesn't feel very useful in this case, encoded in here as submatrices are Terayev's base matrix. So this really is capturing the correct construction of your base matrix for singular flat virtual links. But that extra information about the intersection points proves very useful. However, once we've constructed this, we need some way to move between different singular base matrices that would come from different representatives. So that's the idea of homology. And as I had mentioned towards the beginning, these operations should be generated by what happens for chord diagrams or what happens on surfaces. So with a type 1 move, you have a brand new self-intersection. Depending on which type 1 move you did, you're either going to get a loop, and remember we're starting at the right fork, following until we get back. Here we have a loop which sees no intersection points. This is effectively a trivial element in homology, or it's not necessarily a trivial element in homology, but in terms of the intersection form, it always pairs to 0. If you do the opposite type 1 move, then you're getting a cycle which sees all of the intersection points that component does. So we have this brand new component which acts like the full blue curve in terms of the intersection form. For type 2 move, if we have both arcs living on the same component and you pull one over the other, you have 2 new intersection points which together act like that component of your link. And then if you have two arcs which come from different components and pull one over the other, your new intersection points act not like a copy of one circle or the other, it acts like the pair of them together. So all of this, we have these 4 extension moves which mirror these operations on the representatives of your flat virtual link. All of these come from type 1 and type 2 moves. Those are the ones which add new intersection points or remove them. So we also need to consider the inverse extensions, the inverses of these extensions. But then for type 3 moves, it turns out that if all the arcs are, let me try that carefully. So as long as you aren't doing a singular type 3 move, then this type 3 operation is going to induce an isomorphism on your singular base matrices. So nothing too strange happens. However, if you do have a singular type 3 move, then you need to look at the cycles that you get here. So I've designated them here. We start here, we follow along, and eventually come back. And we need to compare this to the natural associated intersection point here. And if you look at this cycle, it feels very different. So we follow out, we come back in, but if you look very carefully, in terms of the intersection form, the only real difference is on the left here, we had this arc of the green curve which contained no intersection points, whereas on the right, the section that covers the green curve sees all of the intersection points along the green curve. So what we're getting is a copy of that green curve. And now just treating these intersection moves as algebraic operations, we get something that captures our singular type 3 moves. And if we try to use these moves, either extensions or the intersection moves, then we'll find ways that we can potentially reduce the size of our matrix by removing excess elements, but we might have to use intersection moves to reveal them. And as soon as we get to something where no matter how we try to use intersection moves, the result, there's no way to use inverse extensions, then that's our minimal singular base matrix. That's the primitive singular base matrix. And this is a couple classic type of results for base matrices. So if the virtual homotopy classes of two singular flat virtual links agree, then the singular base matrices are homologous. And then what's really nice is that up to a collection of intersection moves, there's actually a unique primitive singular base matrix associated to any representative or to a flat virtual link. So this would be lovely but what's useful about this is that we can actually obtain this primitive singular base matrix in a greedy fashion. It doesn't matter what path you follow to get to the minimal base matrix, so long as you know that there is no way to further reduce its size. And in all of the cases with these with all of these base matrices, you can show that the uniqueness you get can be achieved by very carefully replacing sequences of extensions and intersection moves in clever ways. Now this all came from Turayev's construction of the base matrix, which is really analogous to the construction of the ciphered matrix for a classical knot. So this is some kind of algebraic tool that we can use, and because of the means by which we obtain it and the uniqueness of the primitive singular base matrix, it's something we can practically use. So we want to do that. We want to use the AMR bracket. We want to use these singular base matrices to somehow bound or compute the minimal intersection number. So here is the only singular base matrix I have shown you today. And what I want to convince you of is that it is primitive already. I didn't have to do any work. So G1 and G2 live on the second component, and oh boy, that looks like a copy of S2. So I might need to be a little bit more careful in doing this. All the fun things you realize when you give a talk. But even with that, you're able to apply a type 1 or a M2 inverse move here to get rid of G1. But even with that, it turns out that you're going to have you now have a primitive base matrix, and now we can look at the base matrices for the other two components, and in this case you will see that the singular base matrix is primitive, and that takes a little bit of work and careful construction. But then looking at what this means, well, okay, these primitive singular base matrices, once you show that they're non-isomorphic, then that means that the singular flat virtual links had to be non-homotopic. So there was no way to move one to the other, which for the virtual AMR bracket means that there's no collapsing. So if you look at the virtual AMR operation, you get this as your reduced expression. And now when you look at the terms, you get one value for each one, and that gives you a lower bound of 3 on the minimal intersection number. Since we have a diagram with 3, then this must be the minimal intersection number. And we can generalize this computation to an infinite family related to beta. And in fact, there's a whole collection of infinite families that we can look at that have some different properties. So here's a collection of flat virtual links where the numbers here are representing the number of parallel arrows. So here we have k arrows pulled across, n arcing from one component to the other, and then n going the other way. Here's the family related to beta that I promised, where we have these 3n intersection arrows, 2 self-intersections, and then here's a family which exhibits some symmetry. So here we can kind of exchange, or there's a natural association between identifying one of these n arrows as the distinguished intersection and one of these n arrows as the distinguished intersection. So looking at each family, we can either use the virtual AMR bracket to get an estimate, or the construction I haven't mentioned here, which are the multi-string based matrices, where we're treating intersection arrows in a more discrete fashion. Both of them work phenomenally on the alpha family. What doesn't work so well is the virtual Goldman bracket. So if you virtualize the Goldman bracket, it turns out that's going to vanish here. At least when k is equal to 1. I think it's true, otherwise I just haven't checked. For the beta family, the virtual AMR operation gives you the minimal intersection number of 3n, but the multi-string based matrices are a little too coarse and they only give you an estimate of n. For gamma, we have the reverse kind of consideration. The virtual AMR bracket vanishes, but the multi-string based matrix sees all of those distinct arrows appropriately. So these are the types of results you can obtain where now we know that if I identified any one of these 2n arrows as the singular intersection, it must be distinct from any other by virtual homotopy. But also, we can connect each of these families back to a collection of curves on surfaces and say very definitively that those exhibit the minimal number of intersection points in their homotopy class. So that's fun. I think that's a really cool result. And I really appreciate you taking the time to watch this video, and I welcome any questions or comments you have. So let me conclude with a fair list of references, and I hope to see everyone soon. Take care.